So this video will show you how to create a PLL block using Lattice's Clarity Designer IP block creation tool. We'll run the NEORV32 at 72 megahertz. So to start, just copy the project folder created from part 1 from before. This is the easiest. Rename it to, I don't know, 72 megahertz. Yeah. And I already have Diamond running here. Open. Go back up. Yeah, that is the folder we just created. Work. LDF is the project extension. Open LDF. So this is the design for Clarity. The tooltip font contrast ratio is off, but don't worry about it. Yeah, Clarity Designer. So in the work folder, design name, let's call it PLL 12 to 72 megahertz. Right. We want to make a VHDL project, simplify, verify everything's correct, and create. Hit this window. So this is the PLL blocks. Create. Yeah. PLL instance name. Let's. This is the PLL 12 to 72 megahertz instance. My design approach may not be perfect, but it like gets things working in some sense. 2 megahertz instance, customize. There are a few settings we need to change. So the input frequency of ours is 12 megahertz from the onboard oscillator. And enable higher, we do not need a reference clock. Feedback CLKOP is a good feedback path. Now we desire a frequency of 72 megahertz. So from what I have learned is a multiple of 12 is what works best, especially if you have a tolerance of 0, which I suggest, which I found like works when you want to use it as a system clock. So just say 72 megahertz. It's a multiplier. So I'm using 72 as an arbitrary number because the NPU, which will show you in the future, just it works the best at 72 megahertz. Otherwise, it gets timing errors. So yeah, CLKOP. If you have like more peripherals attached to your system, then you can generate more clocks from the same reference clock. For example, I can just enable it and say, okay, I want a 24 megahertz clock as well for some other peripheral complete, but we don't want it now. Okay, OP. Then we also want like optional ports. So we want to provide a PLL lock signal which is sticky, and yeah, phase, press calculate. It works. If it did not, for example, if I had chosen something arbitrary like I don't know, 44, calculate, cannot be generated, blah blah blah, because of the zero tolerance constraint. We'll just say 72 megahertz, calculate, configure, errors total 0, close, starting, it's running. Generated. Now we have a design in our project hierarchy. This is instance work. Go to input files, create add existing file, implementation 1. Sorry, PL this folder. Now we'll want to add this file. We do not want to copy it because we can just reference it. It's better, so we just say oh, add. Open. Now this is the generated PLL block, 12 to 72 megahertz. Now we'll need to edit the ECP file, EVN boot top level file. This is not the processor template file, the minimal boot template file. This is just the this is our file where we like pass in the FPGA pins etc. to the NEORV32. So we'll instantiate the FPGA block, the PLL block here, and pass that to our NEORV32. So we'll need to update our system clock. So now we are using a 72 megahertz clock. So update to. We'll need to declare a few signals for the PLL. So add it here. Clocks is 72 megahertz clock that will pass to the NEORV32 PLL lock for the lock signal we just created, and the recent reset sync clock synchronizes the PLL lock and the physical reset button we have on the FPGA. So I've gone ahead and created the PLL and clocking signals. There was an extra clock signal below which I deleted and moved it up here. Clock sys, this is the 72 megahertz clock, system clock from the PLL. PLL locked is the lock signal from the PLL block we just created. Recent sync, as I said, synchronizes everything. This is the VHDL logic to combine the reset physical reset button input and the lock signal from the PLL block. And this is the PLL block instantiation. So we are passing in the 12 megahertz clock as input. We are getting a 72 megahertz system clock as output, and this is of course the lock signal. In the NEORV32 instantiation, so in the mapping at clock C, since the variable doesn't matter, clock input, now you use clock sys, and now we are using reset sync instead of the direct reset input from the FPGA. I've gone ahead and generated a bit stream. It's just like run to save time, and we'll open the program. So create a new project, doesn't matter. Okay. Successfully. No. So sometimes it may be the case that especially if you have saved the programmer project, where when you create a new project by copying an older one, the programmer may not select the correct bit stream. So just use the file explorer to correct or select it. It's under the implementation folder, bit stream. Now we'll program it like before. While it's being programmed, we can start running GTK term. Funny, it doesn't. Okay, yeah, see, now it's on USB. Just reset it. Remember to set CRLF auto, and so like before when we ran the first demo, main NEORV32 HAL. Remember, so for the HAL, we need to go to the toml file, lar.toml file. And now, so previously we ran it at 12 megahertz, so we changed the clock speed to that. Now we are running it at 72 megahertz, so we need to set the clock speed to 72 megahertz. Okay, and we can just go back here in the demos example folder, open terminal. You want to clean it, so we don't want any other binaries. Yeah, pins folder. Old stuff's empty, it's just the old executables, which you can it's not necessary to delete them, but I just do. So yeah, first run ALR build, get the data output, then a RISC by 64. Now we have a bias.bin file, and now we have an image, and so a file which we can upload to the NEORV32. NEORV32 setups main, NEORV32 this demos bin bias30xe. Just resize it. You can see it works as before. System info 72 megahertz. All right. Thank you. These files will be found in part 2 of the folder on the repo. The repo will have better instructions on how to navigate stuff because it may change over time. Thank you.